Every second, without pause and without warning, countless invisible messengers travel through your body. You do not feel them, you do not see them, and yet their presence is relentless. Among the most extraordinary of these are neutrinos, particles so elusive that they were once believed to be impossible to detect. Every square centimeter of your skin is crossed by tens of billions of them each moment, streaming from the core of the sun, from cosmic rays colliding in the upper atmosphere, from distant supernovae that erupted long before human beings walked the Earth, and even from the first seconds after the universe was born. Their ghostly passage is constant, and yet you remain completely unaware. The idea that the universe is built mostly from things we cannot see has a long history. When scientists first discovered radiation at the end of the 19th century, they realized that matter could emit energy in forms invisible to the eye. Henri Becquerel noticed strange emissions from uranium salts. Marie and Pierre Curie uncovered polonium and radium, elements that glowed faintly but more importantly radiated an unseen force capable of fogging photographic plates. In those early decades of the 20th century, physicists learned that atoms themselves were not solid, indivisible objects, but miniature solar systems made of electrons orbiting around a dense nucleus. These revelations opened the door to a new truth. What we call the visible world is only a fraction of reality. As experiments advanced, scientists realized that much of nature is hidden in spectra outside human vision. We see only a narrow band of electromagnetic waves, from red to violet light. But radio waves, microwaves, infrared radiation, ultraviolet rays, X-rays, and gamma rays exist beyond those colors. Our eyes evolved to detect only what was most useful for survival on the surface of the Earth, yet the universe shines in many more ways. When physicists built detectors capable of perceiving these other wavelengths, they found that the cosmos is far more active than ordinary sight suggests. Stars, galaxies, and black holes emit streams of energy invisible to our vision, but measurable with instruments. Neutrinos represent an even deeper level of invisibility. Unlike photons, which are particles of light that interact easily with matter, neutrinos almost never collide with anything. They pass through solid rock, metal, or flesh, as though it were transparent space. Trillions pass through the Earth every second. In fact, if you imagine a wall of lead 1 light-year thick, a significant fraction of neutrinos could still tunnel through it without interaction. This is not science fiction, but a direct result of the extremely weak force that governs their behavior. The story of neutrinos is intertwined with the history of particle physics itself. In the early decades of the 20th century, the discovery of the neutron and the proton inside the nucleus was already reshaping science. Physicists realized that the forces binding these particles together must be unimaginably strong, yet during certain radioactive decays, where a neutron transforms into a proton and releases an electron, something was missing. The energy of the emitted electrons did not add up. It appeared that the sacred principle of energy conservation, a foundation of all physics, was being broken inside the atom. The solution came in 1930, when the Austrian physicist Wolfgang Pauli proposed a desperate idea. To save the law of energy conservation, he suggested that another particle must be escaping undetected, carrying away the missing energy. He called it a neutral particle of tiny or zero mass. Enrico Fermi later named it neutrino, meaning little neutral one in Italian. At first, this was only a hypothesis. The particle was so elusive that many doubted it would ever be observed. For more than 2 decades, neutrinos were treated as ghosts in equations, useful for balancing the books, but impossible to confirm. But this ghostly nature is not unique to neutrinos. The universe is filled with particles and forms of energy invisible to us. Cosmic rays, discovered in the early 20th century by Victor Hess during balloon flights high into the atmosphere, bombard the Earth from space constantly. They consist mostly of protons and heavier nuclei, accelerated by violent astrophysical events. When they crash into molecules in the atmosphere, they produce showers of secondary particles, many of them invisible, some of them capable of reaching the ground. Later, astronomers found that even the rotation of galaxies could not be explained by visible matter alone. Something unseen, now called dark matter, must make up most of the mass of the universe. All of this reveals an unsettling truth. What we perceive with our eyes, and even with our most advanced telescopes, is not the majority of reality. Ordinary matter, the atoms that compose stars, planets, air, water, and life, represents only a small fraction of the total cosmic energy budget. Most of the universe is hidden from direct observation. Neutrinos, photons outside the visible spectrum, cosmic rays, and dark matter candidates all belong to this invisible majority. The surface world of color and form that humans experience is only the tip of an immense iceberg, and beneath the surface lies a sea of particles and forces that silently shape the cosmos. Imagine standing outside on a clear night. You see stars glowing faintly in the dark sky, but in that same moment, countless neutrinos are streaming from those stars, slipping effortlessly through your body. Some originated only 8 minutes ago in the nuclear furnace of the Sunday. Others were born in galaxies, millions of light years away. A few may even be remnants from the first second after the Big Bang, still traveling across the cosmos nearly 14 billion years later. They are everywhere, and yet you will never notice them. The realization that the universe is mostly invisible is not simply poetic. It forces scientists to reconsider what it means to study nature. Instruments must be designed to detect the undetectable, to turn faint traces into measurable signals. And with every new detection, the picture of the cosmos becomes both clearer and more mysterious. The human story of science is, in many ways, the story of learning to see what cannot be seen. The transition from visible matter to invisible particles is more than a shift in perspective. It is a revolution in understanding. As the 20th century advanced, it became undeniable that the foundations of physics rested on phenomena hidden from human senses. The next stage of the story would focus on the neutrino itself, a particle born from a desperate attempt to preserve the laws of physics, and destined to become a key to unlocking the mysteries of the universe. The journey deeper into the invisible begins with the early explorers of atomic structure. At the dawn of the 20th century, Ernest Rutherford showed that atoms were not uniform spheres but contained a dense nucleus surrounded by orbiting electrons. Soon after, James Chadwick discovered the neutron, completing the basic picture of atomic nuclei. These findings were revolutionary, but they raised more questions than they answered. How did neutrons and protons transform into each other during radioactive decay? Why did the energies of particles leaving such decays not match expectations? The missing energy problem haunted physicists, and it was within this puzzle that the neutrino was born as a concept. Wolfgang Pauli, who was known for his sharp intellect and uncompromising standards, introduced the idea in 1930, not out of excitement, but out of desperation. In a now famous letter to a group of physicists meeting in Tübingen, he described the possibility of an undetected neutral particle that balanced the equations of beta decay. He admitted that he had done something dreadful by proposing a particle that could not be detected. At that time, physics was guided by the principle that all particles should, in principle, leave a measurable trace. To postulate a ghost particle seemed unscientific, even reckless. Yet Pauli understood that without such a hypothesis, one of the most sacred laws of physics, conservation of energy, would be broken. His humility in presenting the idea was matched by his confidence that nature must be consistent. Enrico Fermi took Pauli's desperate idea and gave it structure. In 1934, he published a theory of beta decay that fully incorporated the new particle. He called it the neutrino, the little neutral one. Fermi's formulation laid the foundation of what later became known as the weak interaction, one of the four fundamental forces of nature. The neutrino thus moved from a ghost in equations to an essential part of theoretical physics. Yet the paradox remained. If neutrinos interacted so weakly, how could they ever be detected? Many believed they never would. For more than 20 years, neutrinos remained invisible assumptions rather than confirmed particles. During those decades, other discoveries revealed just how strange the subatomic world could be. Photons beyond the visible range were mapped out with new detectors, leading to the rise of radio astronomy and X-ray astronomy. Cosmic rays were found to include not only protons but also muons and pions, exotic particles created in high-energy collisions. Nuclear reactors, which came into existence during the 1940s, provided a new kind of laboratory places where enormous numbers of neutrinos were being produced through the fission of heavy nuclei. Physicists began to wonder whether these man-made neutrino sources might offer a chance to detect the undetectable. But to understand why neutrinos seem so impossible to catch, one must grasp just how weakly they interact. Electrons and protons respond to electromagnetic forces, which are billions of times stronger than the weak force. Neutrons and protons also feel the strong nuclear force, which binds atomic nuclei together. Neutrinos, in contrast, feel almost nothing. Their interactions occur through the weak force alone, making them pass through light years of matter with only a small chance of collision. This is why billions pass through your body every second without leaving a trace. To detect them requires unimaginably large volumes of material and exquisitely sensitive instruments. Despite the difficulty, a few daring scientists believed it was possible. Frederick Reinz and Clyde Cowan were among the first to attempt the task in the 1950s. They reasoned that the intense flux of neutrinos from a nuclear reactor might provide a detectable signal if one looked for the rare interactions in a carefully designed detector. Their experiment at the Savannah River plant in South Carolina eventually succeeded, providing the first direct evidence that neutrinos were real. In 1956, Reinz and Cowan announced that they had captured the ghost particle. For Pauly, still alive at the time, the news was a relief. His desperate proposal had been vindicated. The neutrino was no longer only a theoretical necessity. It was a confirmed particle, a genuine part of the physical world. While the confirmation of neutrinos was a landmark, it was only the beginning. Soon, physicists realized that neutrinos existed in multiple varieties, now known as flavors: the electron neutrino, the muon neutrino, and the tau neutrino. These distinctions were subtle but crucial. They hinted at a complexity far greater than the original hypothesis. Even as neutrinos were finally accepted, they remained wrapped in mystery. Meanwhile, other invisible domains of the universe were opening. Astronomers discovered that galaxies rotated faster than expected, evidence for what would later be called dark matter. Physicists probed deeper into cosmic rays, uncovering showers of unseen particles raining down constantly. The sense grew that reality was a layered fabric, with the visible world sitting atop a foundation of invisible phenomena. Each discovery pushed human understanding further from everyday intuition. The universe was revealing itself as a place where most of its contents were beyond direct perception, yet no less real. The recognition of this hidden majority reshaped philosophy as much as science. For centuries, human beings assumed that what they saw represented the essence of reality. The stars in the night sky, the warmth of the sun, the colors of the earth seemed to offer a complete picture. But physics was now showing that the visible was only a sliver. Beneath the surface was a constant flood of radiation, particles, and forces invisible to our senses. Neutrinos were perhaps the most striking example, not because they were the only invisible particles, but because they challenged the very idea of measurability. They demonstrated that nature can hide its workings at levels almost beyond reach. The progression from Pauly's desperate letter to the first detection of neutrinos marked a turning point in science. It proved that patience, creativity, and faith in the consistency of natural laws could reveal even the most elusive phenomena. But it also raised new puzzles. How many types of neutrinos were there? How much did they weigh, if they had any mass at all? And why did the universe seem to be structured in such a way that neutrinos were both ubiquitous and nearly undetectable? These questions would not be answered quickly. They would require decades of experiments, new technologies, and the collaboration of scientists across the globe. As the 20th century moved forward, humanity stood at the threshold of a new era of discovery. The hidden sea of particles was no longer a matter of speculation. It was a fact of existence, as real as the air we breathe. Neutrinos, once a desperate mathematical trick, had become a central part of physics. And with every step, the invisible universe was beginning to reveal itself. The story, however, had only just begun, and the next chapters would uncover mysteries far stranger than anyone had imagined. The revelation that neutrinos existed did not diminish their mystery. If anything, it deepened it. To confirm their existence required extraordinary experimental courage, and yet the confirmation only underlined how little was known. Physicists now had proof that nature was filled with invisible currents, streams of particles flowing freely through all matter. But knowing they were there was not enough. The challenge became understanding what role they played in the wider cosmos. Every second, the nuclear furnace at the core of the Sun releases an immense flood of neutrinos. These are born when hydrogen nuclei fuse into helium, releasing energy that ultimately becomes sunlight. For every photon of visible light that escapes the Sun and warms the Earth, billions of neutrinos have already streamed outward unnoticed. Unlike photons, which take thousands of years to scatter their way from the Sun's core to the surface, neutrinos leave the Sun almost instantly. Their lack of interaction allows them to fly straight through dense matter. By the time a photon that originated in the Sun's heart finally reaches your eyes, the neutrino from that same nuclear reaction has long since sped through you and continued across the galaxy. This property makes neutrinos perfect messengers. They carry information directly from otherwise inaccessible regions of the universe. Yet for decades after their discovery, detecting these messengers remained nearly impossible. The average neutrino is so unlikely to interact that even a massive detector might see only a few events over years of observation. This makes the task of studying them both frustrating and inspiring. When scientists finally recorded the faint flashes of light caused by neutrino collisions, those signals carried the weight of history. Each interaction was a direct communication from processes otherwise hidden behind impenetrable barriers of matter and energy. The growing realization of the invisible universe did not stop with neutrinos. In the mid-20th century, astronomers began to map the cosmos more carefully. They noticed that stars at the edges of galaxies moved faster than gravity from visible matter could explain. Vera Rubin's meticulous measurements of galaxy rotation curves demonstrated that something unseen, later called dark matter, must provide additional mass. This was not a minor correction, but a radical discovery. Ordinary atoms accounted for only a small portion of a galaxy's true mass. The rest was invisible, interacting with light so weakly that it escaped direct detection. At the same time, cosmic ray research uncovered the staggering energies of particles bombarding the Earth from space. Balloons and satellites recorded protons, and atomic nuclei accelerated to speeds close to that of light, energies far beyond anything produced by human technology. These particles hinted at cataclysmic events across the universe: supernova explosions, black hole jets, and perhaps even more exotic phenomena. They too became part of the hidden sea of particles streaming through our planet and through us. Taken together, these discoveries forced a dramatic shift in human understanding. The universe was not a quiet, static backdrop to human life. It was a storm of unseen activity. Neutrinos streamed by in unfathomable numbers. Dark matter shaped the gravitational architecture of galaxies. Cosmic rays bombarded Earth with relentless force. Even the cosmic microwave background, the afterglow of the Big Bang, discovered in 1965, reminded scientists that invisible radiation filled every direction of the sky. The visible stars were only a surface impression of a far deeper reality. For ordinary people, these revelations are not easy to grasp. Our senses evolved to navigate the immediate environment of Earth. We see colors, we hear sounds, we feel textures. None of these senses reveal the floods of particles passing through us every instant. To imagine the invisible requires both scientific imagination and experimental proof. Yet the fact that humans can uncover these hidden truths at all is extraordinary. With instruments of glass, steel, and electronics, we extend our senses into realms nature never intended us to perceive. The hidden sea of particles is not only a scientific curiosity, it is fundamental to the existence of everything we know. Without neutrinos, the nuclear reactions in stars would play out differently. Without dark matter, galaxies might never have formed in the structures we see today. Without cosmic rays, the chemistry of the atmosphere, and even the genetic story of life, might have unfolded along different paths. The invisible is not separate from the visible. It defines it. The awareness of this truth also reshapes philosophy. For millennia, human beings believed that what they saw was the essence of reality. Ancient astronomers mapped the stars and believed the heavens were made of crystalline spheres. Even in the scientific revolution, the focus was on visible phenomena: planets orbiting, apples falling, light refracting. The 20th century broke that illusion. Physics revealed that reality is built from layers hidden beneath perception. Atoms, fields, particles, and forces operate at levels no human eye can see. What we call reality is a projection built from invisible foundations. Standing under the night sky, one might feel alone, gazing up at distant stars. But the truth is that no one is ever alone. At every moment, the universe is in contact with us. Neutrinos, cosmic rays, and other unseen particles are constantly passing through. The very fabric of existence is woven with invisible threads. The silence of the night hides an immense traffic of particles linking every person to the cosmos. By the end of the 20th century, scientists had begun to appreciate the scale of this hidden sea. The Earth itself is bathed in invisible radiation and particles from every direction. Our planet does not shield us from them, because most simply pass through unhindered. Some travel from the depths of space, others from the heart of the sun, others from the radioactive elements inside the Earth itself. Each tells a story of creation and transformation, of energy and matter in constant motion. The story of invisible particles is not only a tale of physics, but also of perspective. To live in the universe is to be immersed in what cannot be seen. The atoms that make up our bodies are transparent to neutrinos. The space between galaxies is filled with dark matter. The cosmos shines in forms of light far beyond human sight. To recognize this is to recognize that the visible world is only a thin surface. Beneath it lies a vast, hidden ocean of activity. As the understanding of this hidden sea deepened, the focus returned to neutrinos. Their existence had been proven, but their nature was still largely unknown. They were everywhere, but they carried secrets scientists had only begun to explore. The discovery that they exist was not the end of the story, but the beginning. And so, the next stage of the journey would ask not whether neutrinos are real, but what they truly are. These questions would challenge the foundations of physics itself. The year was 1930, and physics stood at a crossroads. In laboratories across Europe, experiments on radioactive decay were revealing something troubling. When a neutron inside an atomic nucleus decayed into a proton and emitted an electron, the energies of those emitted electrons were spread over a wide range. According to the principles of conservation that governed physics, each decay should have released a fixed energy. Yet the experimental results stubbornly refused to obey this expectation. It looked as though one of the deepest laws of nature was being violated. For many physicists, the simplest explanation was that the data were incomplete or flawed. Perhaps the measurements were not sensitive enough, or perhaps some subtle correction had been overlooked. But Wolfgang Pauli, a young Austrian physicist already known for his sharp insights, took the problem more seriously. In December of that year, he wrote a letter to a gathering of physicists in Tübingen. His words would later be remembered as one of the boldest proposals in science. To preserve the sacred principle of energy conservation, Pauli suggested that an unknown particle must be escaping detection. It would be electrically neutral, it would have little or no mass, and it would carry away the missing energy from beta decay. He confessed in the letter that he had done something dreadful by proposing a particle that seemed impossible to observe. At the time, the idea was radical. Physics was not in the habit of inventing invisible entities without evidence. Yet Pauli's reputation lent weight to the suggestion, and others began to take it seriously. The mysterious particle quickly became a subject of speculation. Still, many regarded it as a bookkeeping trick, rather than a real entity. It was an idea to save the equations, not something that would ever be confirmed in an experiment. Enrico Fermi, an Italian physicist of extraordinary creativity, saw more than a desperate hypothesis. By 1934, he had constructed a full theory of beta decay that incorporated Pauli's proposal. He gave the invisible particle its name, Neutrino, meaning little neutral one in Italian. Fermi's theory was more than just a patch for a failing law. It was a framework for what would later become known as the weak interaction, a fundamental force alongside gravity, electromagnetism, and the strong nuclear force. The neutrino, once a ghost particle, became essential in describing how matter transforms at its most basic level. Despite the elegance of Fermi's theory, a practical problem remained. If neutrinos interacted so weakly, how could anyone hope to detect them? For decades, the consensus was that they could not be. Pauli himself doubted they would ever be observed. They would remain useful fictions, mathematical phantoms, ensuring that conservation laws remained intact. This resignation persisted until the dawn of the nuclear age, when human technology created a new and powerful source of neutrinos. Nuclear reactors, first built in the 1940s, were found to produce vast numbers of neutrinos as byproducts of fission. Inside the dense core of a reactor, heavy nuclei split apart, releasing energy and streams of particles. Among those particles were trillions upon trillions of neutrinos, pouring out with every second of operation. For the first time, scientists realized they had a man-made source of these elusive particles, a torrent far greater than anything previously accessible. The ghostly particle might, after all, be within reach. Two physicists, Clyde Cowan and Frederick Rines, seized the opportunity. They designed an experiment to detect neutrinos from the Savannah River nuclear reactor in South Carolina. Their plan was ingenious. If a neutrino collided with a proton, it could produce a positron and a neutron. The positron would quickly annihilate with an electron, producing a flash of gamma radiation. The neutron, captured a short time later, would give off another gamma ray. By looking for pairs of flashes separated by microseconds, Rines and Cowan hoped to see the unmistakable fingerprint of neutrino interactions. Their apparatus used large tanks of water mixed with cadmium chloride, lined with detectors sensitive to flashes of light. It was a daring experiment, pushing the limits of what seemed possible. In 1956, after months of careful observation, they announced success. They had seen the ghost particle. The neutrino had been detected. Pauli, still alive at the time, was informed by telegram. His theoretical invention had been vindicated. The dreadful proposal of an undetectable particle had become a confirmed fact of nature. The detection of the neutrino marked a turning point in physics. It showed that even the most elusive predictions could be tested with sufficient ingenuity and persistence. It also underscored the strange nature of the subatomic world, where particles could exist in vast numbers and yet remain almost intangible. The discovery would earn Rines a share of the Nobel Prize decades later, long after Cowan had passed away. But in that moment, in 1956, the doors to an invisible universe had been flung open. Yet the birth of the neutrino was not the end of the story. Almost immediately, new questions arose. How many types of neutrinos existed? Did they have mass, or were they truly massless, as Pauli had suggested? What role did they play in the grand architecture of the cosmos? The ghost particle had stepped out of theory and into reality, but it remained wrapped in mystery. The stage was set for some of the most profound discoveries of the 20th century. The path from Pauli's desperate letter to the detection by Rines and Cowan illustrates the essence of scientific progress. It is not always a straight line. It begins with anomalies, with stubborn facts that refuse to fit. It requires bold hypotheses, sometimes bordering on the outrageous. It depends on the courage of experimentalists willing to build improbable machines to chase improbable signals. And when success comes, it does more than solve a problem. It changes the way humanity sees the universe. The neutrino was not merely a particle added to the list. It was a new way of thinking about reality, proof that the universe is far stranger and richer than common sense would allow. The birth of the neutrino was a scientific revolution. But like every revolution, it brought upheaval. As the second half of the 20th century unfolded, physicists would discover that neutrinos were even stranger than Pauli or Fermi had imagined. They would challenge the foundations of the Standard Model, link the smallest scales of physics to the largest scales of cosmology, and reveal that the universe is built from mysteries we are only beginning to comprehend. The first confirmed detection of neutrinos in 1956 was more than a triumph of experimental technique. It was a profound shift in how scientists approached the unseen world. Pauli's ghost particle had materialized in flashes of light inside tanks of water, proving that even the most reluctant participants in the universe could be coaxed into leaving their trace. Yet those faint signals carried with them an unsettling implication. If neutrinos were everywhere, constantly streaming from the sun, from nuclear reactors, and from the very heart of exploding stars, then humanity was immersed in a sea of particles far beyond its ability to sense directly. The realization dawned slowly. In the years that followed the Rhines and Cowan experiment, physicists refined their methods and confirmed the existence of different varieties of neutrinos. The muon neutrino, associated with the muon discovered in cosmic ray experiments, was identified in 1962 at Brookhaven National Laboratory. Later still, the tau neutrino would be confirmed at Fermilab, completing the triad of known neutrino flavors. Each discovery added weight to the idea that the neutrino family was complex, not a single ghost particle, but a set of ghostly cousins with distinct identities. Even as the family of neutrinos expanded, the central puzzle of their behavior remained. Neutrinos interacted so rarely that entire generations of physicists struggled to capture even modest numbers of them. For every trillion neutrinos that passed through a detector, only a few would announce themselves. This extreme shyness forced scientists to think on scales that bordered on the absurd. Detectors needed to contain thousands of tons of material, shielded from cosmic rays deep underground or under mountains, just to register occasional flashes. It was an era when particle physics began to build instruments of almost geological size, sculpted into the Earth itself, simply to reveal whispers from invisible visitors. The scientific world began to realize that neutrinos were more than curiosities. They were crucial messengers of the universe. From the core of the sun, they streamed outward long before photons could escape, offering a direct window into nuclear reactions hidden beneath hundreds of thousands of kilometers of plasma. From cosmic ray interactions in the atmosphere, they rained down continuously, carrying information about violent collisions at the edge of space. From supernovae, they surged in overwhelming floods, releasing most of the energy of stellar death in the form of neutrino bursts. To study neutrinos was to study the most extreme events in nature, through particles that passed undisturbed through barriers that would stop every other kind of radiation. But there was another reason neutrinos fascinated physicists. They seemed to belong to the very foundations of particle theory. Enrico Fermi's framework of weak interaction was only the beginning. As the Standard Model of particle physics took shape in the mid-20th century, neutrinos became essential players. The model arranged all known particles into families of quarks and leptons, bound together by fundamental forces. In this elegant structure, the neutrino occupied a curious place. It was nearly massless, electrically neutral, and barely interactive. It seemed like a particle that was there because it had to be, not because it wanted to be. This very aloofness hinted that neutrinos might carry secrets about physics beyond the Standard Model. In classrooms and lecture halls, physicists emphasized the paradox. Neutrinos were among the most numerous particles in the universe, second only to photons in abundance. Yet their reluctance to interact made them among the least understood. Every second, around 65 billion solar neutrinos streamed through each square centimeter of Earth, a flood so vast that it defied imagination. And yet, in those same seconds, most detectors around the world would register nothing at all. The ghostly sea was real, but maddeningly silent. Some scientists questioned whether it was worth the effort to chase such unwilling participants. But history proved otherwise. Each time physicists devised a new experiment, neutrinos responded with surprises. They revealed themselves in underground tanks, in bursts from cosmic events, and later in kilometer-scale observatories built in ice and water. Each time, they forced revisions to theory, hinting that the neat picture of the standard model was incomplete. In the decades immediately following their discovery, the focus remained on proving their existence and characterizing their properties. How many flavors were there? Were they truly massless, as Pauli and Fermi had imagined? Could they transform into one another, as some daring theories suggested? These questions were unresolved, and the tools of the mid-20th century were not enough to answer them definitively. Yet the groundwork was being laid for discoveries that would shake physics to its core. The birth of the neutrino, then, was not a single moment, but a sequence. It began with Pauli's desperate attempt to save the laws of physics. It grew with Fermi's bold theory, giving the particle its name and its place in a new force of nature. It became real with Rhine's and Cowan's flashes of light in a South Carolina reactor. And it matured with the recognition that neutrinos came in multiple forms, each with its own elusive identity. What began as an act of desperation had become one of the central stories of modern science. Yet this birth was only the beginning of a much longer tale. In the years ahead, neutrinos would confound predictions, reveal their ability to change identities, and force scientists to confront the possibility that the universe's most elusive particle might hold the key to some of its deepest mysteries. The quiet announcement of their detection in 1956 was not the closing of a chapter. It was the opening line of a saga still unfolding. The emergence of the neutrino as a confirmed particle was both a triumph and a challenge. Once the flashes in Rhine's and Cowan's detector proved that neutrinos existed, the physics community was faced with the daunting task of learning more about them. But learning more about neutrinos was unlike studying any other particle. For protons, electrons, and photons, interactions were frequent enough to allow careful experiments in ordinary laboratories. Neutrinos, in contrast, passed through matter as if it were not there, the very trait that made them essential to preserving the laws of physics, also made them nearly invisible to every attempt at measurement. The early years of neutrino research were marked by a paradoxical combination of certainty and mystery. The certainty came from the fact that neutrinos were clearly real, established by experiment and confirmed by theory. The mystery came from everything that remained unknown. How many types of neutrinos existed? Did they have mass? Or were they massless? How could their presence be reconciled with the emerging standard model of particle physics? These questions hung in the air, unanswered, for decades. In the 1960s, further progress came when scientists began constructing larger detectors deep underground. Shielded from the constant rain of cosmic rays, these detectors could focus on the faint traces of neutrinos. One of the first great attempts was the Homestake experiment, led by Raymond Davis in a gold mine in South Dakota. Using a tank filled with 600 tons of cleaning fluid rich in chlorine, Davis attempted to capture solar neutrinos. The principle was simple in idea, but monumental in scale. The tank inferred if a solar neutrino struck a chlorine atom, it could transform it into argon, a different element. By carefully counting the atoms of argon that appeared over time, Davis hoped to measure the neutrino flux from the sunday. The experiment was painstaking, requiring years of patient work and highly sensitive methods to extract and count just a few atoms of argon. When the results came in, they revealed a puzzling discrepancy. Davis found only about 1/3 of the neutrinos that theory predicted should be arriving from the sunday. The implications were enormous. If the experiment was correct, then either the understanding of the sun's nuclear furnace was flawed, or something far stranger was happening to neutrinos themselves. This enigma became known as the solar neutrino problem, and it would haunt physics for decades. The discovery of the solar neutrino problem demonstrated that the neutrino was not only elusive, but also deeply mysterious. It suggested that these ghost particles might behave in ways no one had anticipated. The problem also marked the beginning of a new era in which neutrinos would repeatedly surprise scientists, refusing to fit neatly into the expectations of established theory. Meanwhile, the discovery of the muon neutrino at Brookhaven in 1962 had already expanded the neutrino family. This showed that neutrinos were not a single particle, but a class of particles linked to different leptons. The existence of more than one type suggested new possibilities for their behavior, including the tantalizing idea that they might be able to transform from one type into another. Such transformations, if real, would mean that neutrinos could not be massless, since oscillations between flavors require differences in mass. For the moment, these were only speculations, but they foreshadowed discoveries that would overturn assumptions about the nature of matter. In parallel with these developments, neutrinos became increasingly important in cosmology. Theoretical work suggested that vast numbers of neutrinos had been produced in the first seconds after the Big Bang. These relic neutrinos, still streaming through the universe today, would outnumber even the photons of the cosmic microwave background. If their properties could be measured, they might offer clues to the earliest moments of cosmic history. In this way, the humble neutrino, born in an act of theoretical desperation, had become a bridge between the smallest scales of particle interactions and the largest scales of cosmic evolution. The story of the neutrino's birth, then, is more than the tale of a single experiment or a single discovery. It is a story of how science responds to contradictions. When confronted with the apparent violation of conservation laws in beta decay, Pauli did not abandon those laws. Instead, he imagined a new particle that would preserve them. When Reiners and Cowan set out to test this improbable hypothesis, they refused to be deterred by the belief that detection was impossible. Their success showed that persistence and ingenuity could reach even into the invisible heart of nature. By the close of the 20th century's first half, neutrinos had emerged as indispensable components of physics. They were real, they were numerous, and they were strange. They streamed endlessly from the sun, from stars, from reactors, from cosmic events, and from the very birth of the universe. And yet, their nature was so poorly understood that each experiment seemed to raise more questions than it answered. The neutrino was both a solved problem and a new mystery. This duality made neutrinos a symbol of modern physics itself. They were proof that science could make the invisible visible, that patience and creativity could reveal truths hidden from the senses. But they were also a reminder that every answer opens a door to deeper questions. The birth of the neutrino was not the end of the story, but the beginning of a mystery that continues to this day. The next stage in the saga would focus on neutrinos in numbers: how many exist, where they come from, how frequently they stream through matter, and what their abundance tells us about the structure of reality. From solar neutrinos to relic neutrinos from the Big Bang, the sheer flood of these particles reveals the immensity of the invisible universe. The neutrino, once doubted as a mere invention, had become one of the most abundant citizens of the cosmos. The discovery that neutrinos exist was astonishing in itself, but the next revelation was even more staggering. They are everywhere, in numbers so vast that the human mind struggles to grasp them. Unlike protons and electrons, which form the building blocks of ordinary matter, neutrinos are not confined to atoms or bound within structures. They roam freely, created in immense floods by nuclear reactions inside stars, by cosmic rays colliding with Earth's atmosphere, by radioactive decay within the planet's crust, by nuclear reactors, and even by the searing conditions of the early universe. The result is a universe saturated with neutrinos, a hidden ocean of particles passing through every planet, every star, and every living thing. Perhaps the most immediate and important source of neutrinos for humanity is the Sunday. In its core, hydrogen fuses into helium through nuclear reactions that power the star's brightness. Each of these reactions produces neutrinos that escape in an instant, traveling outward at nearly the speed of light. By the time photons of sunlight reach Earth, their journey has taken thousands of years, bouncing and scattering inside the dense plasma of the sun before finally emerging at the surface. Neutrinos from those same reactions, however, reached Earth just 8 minutes after being born, unhindered by matter. It is estimated that every square centimeter of Earth is bombarded by about 65 billion solar neutrinos each second. Pause for a moment, hold your hand up, and consider that billions of particles are passing through your palm every instant, whether you are standing beneath the midday sun or sitting in the dark of night. But the sun is only the beginning. High above the Earth, cosmic rays charged particles from distant sources in the galaxy and beyond strike molecules in the atmosphere with immense energy. These collisions create showers of secondary particles, including pions and muons, which decay into neutrinos. The result is a constant rain of atmospheric neutrinos that fall from every direction. These particles are less numerous than solar neutrinos, but often more energetic, carrying with them the signatures of violent astrophysical accelerators. To study atmospheric neutrinos is to study the physics of cosmic rays and the extreme environments that hurl protons across interstellar and intergalactic space. Closer to home, the Earth itself is also a source of neutrinos. Deep in the planet's crust and mantle, radioactive isotopes of uranium, thorium, and potassium undergo decay, releasing heat that drives geological processes. In each decay, neutrinos called geoneutrinos are emitted. Although their flux is far smaller than that of solar or atmospheric neutrinos, they are direct messengers from the hidden interior of the Earth. Detecting them allows scientists to study the heat budget of the planet, understanding how much of Earth's internal warmth comes from radioactive decay versus residual heat from planetary formation. In this way, neutrinos provide a unique window not only into the cosmos, but into the very ground beneath our feet. Human activity adds another source to this invisible flood. Nuclear reactors, operating around the world, are powerful factories of neutrinos. Every second, trillions upon trillions stream from their cores as atoms split in fission. These reactor neutrinos are not just byproducts, they have become essential tools of science. By measuring them, physicists can monitor reactor performance, test theories of particle physics, and even explore the possibility of detecting clandestine nuclear activity. The same technology that confirmed Pauli's desperate idea now helps safeguard international agreements and provides data for some of the most precise experiments ever designed. Perhaps the most remarkable source of neutrinos, however, lies not in stars, reactors, or radioactive rocks, but in the earliest moments of time itself. Just 1 second after the Big Bang, when the universe was a seething plasma of particles and energy, neutrinos streamed free. These relics of creation, known as the cosmic neutrino background, still permeate the cosmos today. Their existence is predicted with overwhelming confidence by cosmology, and although they have not yet been directly detected, their fingerprints are imprinted in the large-scale structure of galaxies and in the subtle fluctuations of the cosmic microwave background. If they are ever measured directly, they will offer a glimpse into the infancy of the universe, a time long before the first atom had formed. What makes neutrinos extraordinary is not just their abundance, but their rarity of interaction. The Earth is constantly bombarded by solar neutrinos, yet almost all pass straight through. To get a sense of scale, imagine that you could build a wall of solid lead stretching for 1 light year. Even such an impossible barrier would only stop a fraction of the neutrinos streaming through it. This strange combination, neutrinos being among the most abundant particles in the universe and yet the least likely to interact, makes them unique among nature's ingredients. They are both everywhere and almost nowhere at once. Occasionally, however, a flood of neutrinos does make itself known in spectacular fashion. In February 1987, a star in the Large Magellanic Cloud, a small galaxy orbiting our own, exploded in a supernova. The event, known as supernova 1987A, was the brightest visible supernova in nearly 4 centuries. Yet long before its light reached Earth, detectors deep underground had already registered a burst of neutrinos. Within just a few seconds, several observatories recorded dozens of events, a flood compared to the usual silence. These neutrinos carried away nearly all of the energy released by the collapsing star, escaping the dense core before light could follow. For astronomers, this was a revelation. It confirmed that supernova explosions are dominated by neutrino emission and proved that neutrinos can serve as advanced messengers of cosmic cataclysms. From the steady drizzle of solar neutrinos to the rare storms of supernova bursts, the numbers paint a clear picture. The universe is not empty. It is filled to the brim with invisible particles. Every human being lives submerged in a cosmic tide of neutrinos, an ocean whose waves pass through mountains, oceans, and flesh as if they were shadows. The challenge for science has never been finding neutrinos, they are all around us, but rather convincing them to speak. For that, detectors must be built on an extraordinary scale, and patience must stretch across years. But when neutrinos do reveal themselves, they tell stories that no other messenger can. The recognition of their abundance set the stage for the next era in physics. Once scientists understood how many neutrinos existed and where they came from, the next question became how to catch them. This challenge would inspire some of the most ambitious experiments of the 20th century, carried out deep underground, under mountains, in Antarctic ice, and in vast caverns filled with pure water. Humanity was about to embark on the great chase for the universe's ghostliest inhabitants. The sheer abundance of neutrinos is difficult to comprehend. To say that 65 billion solar neutrinos pass through every square centimeter of Earth each second is an astonishing number, but numbers on this scale strain human imagination. One way to think of it is this: hold out your hand, palm upward, and in the time it takes to blink, more neutrinos have passed through it than there are grains of sand on all the beaches of the world. And yet, you do not feel a thing. No warmth, no tingling, no pressure. These countless visitors leave no mark, because they almost never interact with the matter they traverse. Why is this the case? It comes down to the nature of the weak interaction, the fundamental force that governs how neutrinos behave. Unlike electromagnetism, which binds atoms and allows light to shine, or the strong force, which glues protons and neutrons inside atomic nuclei, the weak force is extraordinarily feeble. The probability of a neutrino colliding with a particle in your body is vanishingly small. Most neutrinos will pass through the entire Earth as though it were transparent space. For them, a planet thousands of kilometers thick is no more of an obstacle than a puff of smoke is to a beam of light. This balance of abundance and invisibility has profound consequences for science. On one hand, neutrinos are the most common particles in the universe, aside from photons. On the other hand, their refusal to interact makes them almost impossible to study. Imagine standing in the middle of a torrential rainstorm, yet only a single drop of water strikes you every century. That is what it feels like to try to catch neutrinos in a detector. Their presence is overwhelming in number but elusive in evidence. Yet nature sometimes offers moments when neutrinos cannot be ignored. Supernovae are one such event. When a massive star exhausts its nuclear fuel, its core collapses under gravity, crushing protons and electrons into neutrons and liberating a flood of neutrinos. In that catastrophic instant, neutrinos carry away nearly all of the energy of the star. The collapse would not proceed as it does without them. The explosion itself is largely a neutrino-driven event. Supernova 1987A revealed this dramatically, when detectors around the world captured a handful of neutrinos that arrived hours before the first visible light from the blast. Those particles had traveled across 168,000 light-years to deliver their message, slipping through both the dying star and intergalactic space without obstruction. The numbers involved in such cosmic events are staggering. In a single supernova, around 10 to the power of 58 neutrinos are released. That is more than the number of grains of dust in all the deserts of Earth. more than the number of stars in the observable universe, by an unfathomable margin. Almost none of those neutrinos will ever be detected by human instruments, but their presence shapes the fate of the star and, by extension, the evolution of galaxies. Each dying star becomes a beacon of invisible particles, scattering neutrinos across space for eternity. Back on Earth, the challenge has been to capture even a tiny fraction of the ordinary flux of neutrinos streaming from the Sun and the atmosphere. The Homestake experiment, operating in the late 1960s, represented one of the earliest and most ambitious attempts. For years, Raymond Davis meticulously extracted and counted a few atoms of argon produced by solar neutrino interactions in his underground chlorine tank. Despite the extreme patience required, the experiment delivered one of the most important results in physics. The count of solar neutrinos was far lower than expected. This deficit did not mean that the Sun was failing in its nuclear burning. Instead, it hinted at something mysterious about neutrinos themselves. The solar neutrino problem, as it became known, suggested that neutrinos might not be static identities, but could transform in flight. Even atmospheric neutrinos provided surprises. As detectors became larger and more sensitive, scientists began to notice anomalies in the ratios of different neutrino types produced by cosmic ray collisions. These irregularities, first regarded as possible experimental errors, would eventually be recognized as clues to a phenomenon even stranger than Pauli or Fermi had ever imagined. To appreciate the scale of neutrino abundance, it helps to consider their contribution to the overall energy content of the universe. While neutrinos themselves are lightweight, possibly almost massless, their sheer numbers mean that collectively they form a significant cosmic population. The relic neutrinos from the Big Bang alone are thought to number in the hundreds per cubic centimeter throughout space. Right now, as you sit and read, a cosmic background of ancient neutrinos is flowing through you, remnants from an era when the universe was less than 1 second old. They are silent passengers, older than stars, older than galaxies, and older than any atom. The paradox of neutrinos is thus written in their numbers. They are the most numerous particles in existence, and yet among the hardest to measure. Their abundance ensures they shape the dynamics of stars, the cooling of supernovae, and even the growth of cosmic structures. Their elusiveness ensures that every insight into their behavior comes only through monumental effort. The balance between these two facts, ubiquity and invisibility, defines the character of neutrino science. By the latter half of the 20th century, it was clear that humanity lived in a universe dominated by unseen currents of neutrinos. The task of physics was to build instruments large enough, sensitive enough, and patient enough to catch them. This ambition would lead to vast underground chambers filled with pure water, to arrays of sensors frozen deep within Antarctic ice, and to global collaborations dedicated to catching even a handful of neutrinos each year. In the faint flashes of light produced by these rare interactions, the universe itself would begin to speak in a new voice. The pursuit of neutrinos soon became a struggle between the immensity of their numbers and the near impossibility of capturing them. Every second, oceans of neutrinos swept through the Earth, yet only the rarest collisions left a mark in detectors. The physics community began to think on scales that had previously seemed unimaginable. To catch these ghostly particles, one needed not just clever design, but immense patience and detectors of extraordinary size. By the 1970s, underground laboratories around the world were searching for signals. Each approach relied on a simple idea. If even a few neutrinos out of the trillions upon trillions could be persuaded to interact with matter, the resulting signals could be amplified and studied. In practice, this meant filling caverns with thousands of tons of target material, whether it was water, cleaning fluid, or heavy liquid scintillators, and surrounding it with instruments sensitive to faint flashes of light. These experiments were shielded from cosmic rays by mountains or kilometers of rock, creating sanctuaries where the whispers of neutrinos could be distinguished from the noise of more ordinary particles. The results were often humbling. A tank the size of a building, operating for months, might detect only a few neutrinos. Yet each detection was a triumph, a reminder that the invisible ocean was real. The data collected revealed fluxes that matched or challenged theoretical predictions, pushing scientists to refine their models of both neutrinos and their sources. The deficit in solar neutrinos, first revealed by the Homestake experiment, refused to go away. Independent detectors confirmed that something strange was happening between the heart of the Sun and the detectors on Earth. Meanwhile, calculations of the neutrino flux from reactors and from atmospheric collisions suggested numbers that were vast but consistent. In the atmosphere, for example, cosmic ray collisions produce showers that yield millions of neutrinos over the Earth every second. In reactors, billions upon billions stream out every instant. The numbers made clear that the challenge was not in the availability of neutrinos, but in our ability to detect them. It was like living beside a roaring ocean, but hearing only the faintest splash now and then. One of the most profound demonstrations of neutrino abundance came not from the steady fluxes of the Sun or reactors, but from sudden cosmic explosions. Supernova 1987A was a milestone because it revealed that nearly all the energy of such an explosion escapes as neutrinos. The burst that reached Earth carried more information about the death of the star than the light itself. In fact, by comparing the timing and energy of the neutrinos detected, physicists could reconstruct details of the collapsing core. This single event showed that even though neutrinos interact rarely, their numbers and energy are so great that in the right circumstances they dominate cosmic processes. The flood of neutrinos in the cosmos is not limited to astrophysical events. Cosmology teaches us that in the first second after the Big Bang, when the universe was unimaginably hot and dense, neutrinos were produced in staggering numbers. As the universe expanded and cooled, these neutrinos decoupled and began to stream freely through space. Today, nearly 14 billion years later, they are still with us, forming the cosmic neutrino background. Although they have not been measured directly, their presence is imprinted in the way galaxies cluster and in the fine details of the cosmic microwave background radiation. It is estimated that there are about 300 relic neutrinos per cubic centimeter of space, meaning that even the emptiest regions of the universe are filled with them. Their total abundance exceeds that of protons, neutrons, or electrons by many orders of magnitude. This realization changes how we think about matter itself. To most people, the universe appears to be made of stars, planets, and galaxies, visible structures composed of ordinary atoms. Yet in terms of particle counts, atoms are an afterthought. Neutrinos, unseen and silent, vastly outnumber all the familiar constituents of matter. They are the true citizens of the cosmos, far more numerous than anything we can touch or see. The universe is, in a very real sense, a neutrino sea, with islands of ordinary matter floating within it. Despite their near invisibility, neutrinos have begun to leave measurable imprints on human technology and imagination. They are used to monitor the operations of nuclear reactors from afar, since the flux of neutrinos reveals the activity inside. They are employed as probes of the Earth's interior, since geoneutrinos provide direct information about radioactive decay in the mantle, and they serve as messengers from the most violent astrophysical events, carrying stories from places no photon could escape. Yet with all this abundance, the story remains one of rarity. For scientists, every detection is precious because it represents an intersection between the immeasurable flood and the tiny chance of interaction. The irony is profound. Billions upon billions of neutrinos flow through your body every second, but the number of times one will interact with a particle inside you in your lifetime is effectively zero. You live immersed in a storm of invisible matter, but you remain untouched by it. The tension between vast abundance and near impossibility has defined neutrino science from its beginning. It is what made Pauli doubt his own proposal, what made Fermi's theory seem bold, and what made Rhinus and Cowan's detection so revolutionary. It is also what propelled the building of immense underground observatories, each one designed to catch the faintest whisper of interaction. As the 20th century progressed, The accumulating evidence from these detectors pointed to a startling possibility. The missing solar neutrinos and the odd ratios of atmospheric neutrinos suggested that neutrinos might not be immutable particles at all. They might be shapeshifters, capable of changing their identities as they traveled. This idea, called neutrino oscillation, would eventually transform physics. But in the era of the 1970s and 1980s, it was still a daring hypothesis. The numbers did not lie, however. Something extraordinary was happening with the most numerous particles in the universe. The story of neutrinos in numbers is therefore more than a tale of statistics. It is a reminder that abundance and importance do not always coincide with visibility. The particles that pass unnoticed through your hand every second, the ones that outnumber all the atoms in your body, may also hold the key to mysteries of cosmic evolution, stellar death, and the nature of matter itself. The universe speaks in neutrinos, endlessly and everywhere, and humanity is only just beginning to learn how to listen. The flood of neutrinos washing through Earth was undeniable, but knowing that they existed and that they were everywhere did not make them easier to study. If neutrinos were going to reveal their secrets, scientists would need to build instruments on a scale never before attempted. The ordinary laboratory was far too noisy, filled with the distracting signals of cosmic rays and radioactive backgrounds. To listen for neutrinos required silence, and silence in this sense meant going deep underground or under vast stretches of water and ice, hiding from the noise of the surface world. The first great leap into this hidden domain came with the homestake experiment in South Dakota. Raymond Davis, already patient by nature, understood that the sun's neutrinos might be caught if one simply provided enough target atoms and enough time. He filled a tank with 600 tons of perchloroethylene, a cleaning fluid rich in chlorine, and lowered it more than a kilometer underground in the homestake gold mine. The principle was simple. A solar neutrino colliding with a chlorine nucleus could transform it into an argon nucleus, releasing an electron. Each new atom of argon was a whisper from the Sunday. The challenge was that these events were extraordinarily rare. Over a month of operation, Davis might capture only a few dozen atoms. To isolate them, he used delicate chemical processes to extract the argon, and then counted the atoms one by one. This painstaking work continued for decades, and the results were both frustrating and profound. Time after time, Davis found far fewer neutrinos than theory predicted. Instead of confirming the expected flux from the sun, his results showed only about 1/3 of what was expected. The solar neutrino problem was born. Was something wrong with the understanding of nuclear fusion in the sun's core? Or was something happening to neutrinos themselves as they traveled through space? The experiment gave no answers, only questions. Yet it established the model for how neutrino research would proceed. Immense patience, immense scale, and immense humility before the faintest of signals. As other teams around the world joined the chase, new technologies expanded the search. In Japan, the Kamiokande experiment used a different approach. Instead of chlorine, it relied on a massive tank filled with pure water, buried deep under a mountain. Around the tank, photomultiplier tubes, a kind of supersensitive electronic eye, watched for tiny flashes of blue light, called Cherenkov radiation. This light is produced when a particle moves through water faster than light can travel through that medium. When a neutrino collided with a water molecule, it could set loose a charged particle that produced this telltale flash. The principle was elegant, and the execution was astonishing. Imagine standing in a cavern with walls covered by thousands of light detectors, all staring into a pool of water the size of a cathedral, waiting for faint sparks from the universe's most elusive messengers. Kamiokande proved its worth dramatically in February 1987, when it detected neutrinos from the supernova in the Large Magellanic Cloud. A handful of flashes in its water tank revealed the core collapse of a star 168,000 light-years away. It was a historic moment. Neutrino astronomy was born. For the first time, humanity had detected a cosmic event, not through light, but through ghostly particles that had traveled across space, nearly unimpeded. The success of Kamiokande inspired an even larger successor, Super Kamiokande. Built in the 1990s, it used 50,000 tons of ultra-pure water and 11,000 photomultiplier tubes, all buried deep beneath Mount Ikeno. With this scale, Super Kamiokande became one of the most powerful eyes ever constructed for neutrinos. It confirmed atmospheric neutrino anomalies that hinted at oscillations, and it provided detailed measurements of solar neutrinos. The image of divers working inside the immense cavern, surrounded by rows of spherical light detectors, became an icon of modern physics. Meanwhile, on the other side of the world, Canadian scientists constructed the Sudbury Neutrino Observatory. Instead of water, they used 1,000 tons of heavy water, in which hydrogen atoms carry an extra neutron. This allowed the detector to measure not just electron neutrinos, but also total neutrino flux across all flavors. When Sudbury's results came in, they provided the long-sought explanation for the solar neutrino problem. The missing neutrinos were not gone. They had simply changed flavor on their journey from the Sun to Earth. This discovery confirmed the phenomenon of neutrino oscillations and proved that neutrinos have mass. It was one of the greatest breakthroughs in particle physics of the late 20th century, and it began in a cavern 2 kilometers beneath the Earth's surface. The pattern was clear. To chase neutrinos, one had to build immense instruments, bury them deep below the surface, and wait for faint signals. These experiments demanded collaboration across nations, enormous investments of time and resources, and a willingness to accept that months of silence might yield only a handful of events. Yet each event carried a significance out of all proportion to its rarity. They were whispers from the sun, from the atmosphere, from distant stars, and from the earliest moments of the universe. But as ambitious as these underground detectors were, an even bolder idea was taking shape. If water in a tank could reveal neutrinos, then why not use a natural volume of water or ice on a colossal scale? Why not turn the planet itself into a detector? This question would lead scientists to Antarctica, to a place where the frozen continent could become one of the greatest observatories in human history. The idea of using natural environments as vast neutrino detectors was not born overnight. It grew out of necessity. Even with thousands of tons of water or heavy water in underground tanks, the number of neutrinos captured remained small. The universe sent endless floods, but only the tiniest fraction left a trace. To study neutrinos at higher energies, or to glimpse them from violent astrophysical sources, required a leap in imagination. Instead of building ever larger containers, what if scientists used the Earth's own materials as the container? The concept took shape in the 1970s, when physicists began exploring the possibility of detecting neutrinos in the deep ocean or in natural ice. Water and ice are abundant, transparent to light, and stable over immense volumes. If photomultiplier tubes could be lowered into such environments, then the ocean or a glacier could serve as the medium, with sensors listening for the faint Cherenkov flashes produced by secondary particles from neutrino interactions. It was an audacious vision: transform the planet itself into an observatory. The first steps were tentative. Experiments in lakes and seas proved that light could indeed travel long enough distances through water for detection to be practical. In the 1990s, Russian physicists deployed strings of detectors in Lake Baikal, the deepest freshwater lake in the world. The Baikal Neutrino Telescope demonstrated that natural water could serve as an effective neutrino observatory. Similar projects began in the Mediterranean, laying the groundwork for what would later become the KM3 NET telescope, an immense array of sensors spread across cubic kilometers of ocean. But it was Antarctica that offered the most extraordinary opportunity. Beneath the South Pole lies a sheet of ice more than 2 kilometers thick, clear, ancient, and stable. If detectors could be embedded deep into that ice, then the continent itself could become the foundation of the world's largest neutrino telescope. The vision was bold, and the project that followed became one of the defining achievements of modern physics. IceCube. Construction of the IceCube Neutrino Observatory began in the early 2000s. Engineers drilled narrow holes into the ice using hot water, reaching depths of more than 2 kilometers. Into each hole, they lowered a string of optical sensors, each one encased in a glass sphere, designed to withstand crushing pressure and extreme cold. Over several years, 86 strings were deployed, each holding 60 sensors, for a total of more than 5,000 instruments. The result was a cubic kilometer of Antarctic ice, instrumented to watch for the faint blue flashes of Cherenkov light. IceCube was not built to capture the ordinary drizzle of solar neutrinos. Its purpose was to look for the rare, high-energy neutrinos born in cosmic accelerators, blazars, quasars, gamma-ray bursts, and perhaps the environments near black holes. These neutrinos, carrying energies millions or even billions of times greater than those from the Sun, were expected to arrive on Earth in vanishingly small numbers. Yet they carried the promise of revealing processes far more extreme than anything a laboratory on Earth could reproduce. When IceCube began operations in 2010, it quickly proved its worth. In 2013, the observatory announced the detection of the first high-energy astrophysical neutrinos. Two events, nicknamed BERT and Ernie with tongue-in-cheek humor, had energies above 1 peta, electron volt, far beyond anything solar or atmospheric sources could provide. These detections confirmed that IceCube had opened a new window on the universe. For the first time, scientists were observing neutrinos born in cosmic engines, billions of light-years away. The achievement was profound. For a century, astronomy had relied on photons light of different wavelengths to study the cosmos. More recently, cosmic rays and gravitational waves had added new messengers. With IceCube, neutrinos joined this family of cosmic probes. Unlike photons, they were not absorbed or scattered by dust and gas. Unlike charged cosmic rays, they were not deflected by magnetic fields. Neutrinos pointed straight back to their sources, carrying clean messages from environments otherwise hidden. The scale of IceCube is staggering, but it is also a symbol of the lengths to which humanity will go to listen to the universe. A cubic kilometer of Antarctic ice, instrumented with thousands of sensors, dedicated to waiting for the rarest whispers of ghost particles. Each detection is a miracle of patience, the culmination of billions of neutrinos ignored for the sake of one that interacts. And yet, those rare events have already changed how we understand the cosmos. But IceCube is not alone. Plans for the Mediterranean Telescope, KM3NET, for upgrades to Lake Baikal arrays, and for future extensions of IceCube itself, all point to a new era of neutrino astronomy. These massive detectors are not only about size, they represent the realization that to understand the universe, humanity must think on planetary scales, using oceans, lakes, and polar ice as instruments. In chasing neutrinos, the Earth itself becomes a tool of discovery. Still, the underground and under-ice observatories revealed more than just cosmic messengers. They also confirmed that neutrinos themselves are not what they first seemed. The experiments began to show that neutrinos were capable of transformations no one had expected. The elusive particles born from Pauli's desperate idea were about to become the heralds of a deeper mystery, the discovery that neutrinos could change their identities, and that, contrary to long-held assumptions, they must have mass. The pursuit of neutrinos through underground caverns and frozen deserts became one of the great adventures of modern science. Each experiment was a monument to patience, built on the recognition that the most abundant particles in the universe reveal themselves only rarely. The home-stake tank of cleaning fluid, the immense chambers of Kamiokande and Super Kamiokande, the heavy water of Sudbury, and the cubic kilometer of Antarctic ice at IceCube were all variations on the same theme: create an immense stage and wait for the faintest trace of interaction. The results transformed neutrino science from speculation to a new kind of astronomy. Each detection was not just a particle event. It was a message from the heart of a star, from the upper atmosphere, or from the farthest reaches of the cosmos. The neutrinos from supernova 1987A were a turning point, proof that neutrino detectors could act as telescopes. A few dozen events, spread across detectors in Japan, the United States, and Russia, carried more physical insight than thousands of nights of starlight. They confirmed that collapsing stars release nearly all of their energy in neutrinos, and they showed that neutrinos escape long before photons, providing advance notice of cosmic death. Kamiokande, with its cathedral-like cavern of water and its forest of photomultiplier tubes, became a central player in this new field. It confirmed the deficit of atmospheric neutrinos, revealing that something extraordinary was happening to neutrinos in flight. The Sudbury Neutrino Observatory, with its heavy water, delivered the critical proof that solar neutrinos were not vanishing, but transforming into different flavors. Together, these results showed that neutrinos oscillate between electron, muon, and tau types as they travel. The solar neutrino problem was not a failure of stellar physics, but a revelation about the nature of the particles themselves. This discovery carried staggering implications. Oscillation requires that neutrinos have mass. Yet the standard model of particle physics, the elegant framework that had organized quarks and leptons into a consistent theory, assumed neutrinos were massless. The confirmation that they possessed mass, however tiny, meant that the standard model was incomplete. The most elusive particles in the universe had managed to break one of the strongest assumptions in physics. It was a triumph of experiment over theory, a reminder that even the most successful models must bow to evidence. IceCube added another layer to the story by extending neutrino detection to the highest energies. Its cubic kilometer of Antarctic ice became a new kind of telescope, capturing neutrinos from blazars and other distant cosmic engines. In 2017, IceCube traced a high-energy neutrino back to a blazar known as TXS 0506 plus 056, billions of light-years away. For the first time, humanity had pinpointed a source of cosmic neutrinos, proving that these ghostly particles could carry direct messages from the most violent astrophysical accelerators. Neutrino astronomy was no longer a dream, but a reality. The scale of these achievements cannot be overstated. From the delicate extraction of a handful of argon atoms in the homestake tank to the flashes of light in Antarctic ice, neutrino research had evolved into a global enterprise. Thousands of scientists collaborated across continents to build detectors, analyze signals, and interpret the faintest data. Each experiment demanded faith that the silence of years would one day be broken by whispers from the invisible universe. And that faith was rewarded. Yet the story was not simply one of triumph. Every answer about neutrinos opened new questions. How exactly do neutrinos acquire their mass? Are there only 3 flavors? Or do sterile neutrinos exist, hidden from detection, but influencing oscillations? Could neutrinos explain why the universe contains more matter than antimatter? A puzzle that has confounded physics for decades. These questions emerged directly from the experiments that revealed neutrino oscillations and mass. The very detectors that proved neutrinos exist in abundance also revealed that they behave in ways not predicted by theory. By the end of the 20th century, neutrino research had reshaped physics. The ghost particle that Pauli proposed in desperation had become one of the most powerful tools for exploring the cosmos. Neutrinos were no longer merely invisible participants. They were active messengers, carrying information from places no light could reach. They had already rewritten the standard model and promised to reveal even deeper mysteries. The chase for neutrinos, carried out in caverns, mines, mountains, lakes, and ice, revealed a truth as profound as any in science. The invisible is not unreachable. With enough imagination, with enough patience, and with enough collective effort, humanity can catch even the rarest whisper of the universe. Each captured neutrino is a thread, and together these threads weave a new tapestry of reality, one in which the unseen dominates the seen. The stage was now set for the next chapter. The detectors had proven that neutrinos exist in abundance, that they oscillate between flavors, and that they carry mass. The question that followed was perhaps the most profound of all. What do these revelations mean for the fundamental laws of physics? The answer would unfold in a new chapter, as neutrinos challenged the very framework that scientists believed was unshakable. The story of the neutrino began as an attempt to preserve order in the laws of physics. It became a story of disruption. For decades, physicists believed they understood the subatomic world with comforting precision. Protons and neutrons made up atomic nuclei. Electrons orbited them, and energy was conserved in every process. When Wolfgang Pauli proposed the neutrino in 1930 to save the principle of energy conservation in beta decay, it was a desperate act of theoretical bookkeeping, a ghost particle invented to balance an equation. Yet this ghost, once brought into existence, refused to stay confined to theory. It became one of the most mysterious and essential ingredients of the universe. By the mid-20th century, experiments had confirmed that neutrinos were real. They streamed from nuclear reactors, from cosmic rays striking the atmosphere, and from the heart of the Sunday. They interacted so weakly that billions of them passed through every square centimeter of Earth each second, yet only rarely left a trace. Their existence was strange enough, but for a while, physicists believed they could at least classify them neatly. There were three flavors: electron, muon, and tau, each paired with a corresponding charged particle. According to the Standard Model, the neutrino was massless. This property made sense. If neutrinos traveled at the speed of light, their tiny interactions and their role in maintaining conservation laws all fit perfectly. The equations closed, the model was elegant, and the world seemed complete. But the universe is not concerned with elegance. In the 1960s, a quiet mystery began to undermine this perfect picture. Deep beneath the ground, in the Homestake mine of South Dakota, the chemist Raymond Davis Jr. and the astrophysicist John Bahcall began one of the most patient experiments in the history of science. Using a massive tank filled with 600 tons of cleaning fluid perchloroethylene, they sought to capture neutrinos produced by nuclear reactions inside the Sunday. The reactions that power the sun's fusion of hydrogen into helium should produce an enormous flux of electron neutrinos, passing through Earth by the trillions every second. If the theory of stellar fusion was correct, Davis's detector should have recorded a predictable number of events. But when the first results came, the count was far lower than expected. Only about 1/3 of the predicted neutrinos were detected. At first, physicists suspected an error, perhaps in the chemistry, perhaps in the calculations. But the discrepancy persisted. Other detectors were built, using different materials and techniques. They all saw the same result: too few solar neutrinos. Either the understanding of the sun's fusion process was wrong, or something strange was happening to the neutrinos themselves. This puzzle became known as the solar neutrino problem, and it haunted physics for decades. The sun's output was consistent with theoretical predictions and with all other observations. There was no reason to doubt that fusion in the sun's core was working as expected. The missing neutrinos had to be explained in some other way. Slowly, a revolutionary idea took shape that neutrinos were not stable in flavor. They could transform from one type into another as they traveled through space. If the detectors on Earth were sensitive only to electron neutrinos, and some of them had changed into muon or tau neutrinos on their journey, that would explain why the measured flux was too low. The idea was radical, because flavor change implied that neutrinos have mass. In quantum mechanics, oscillation between states occurs only when those states have different energies, and different energies imply different masses. But in the Standard Model, neutrinos were massless. To admit that they had mass was to admit that the model was incomplete. It meant that one of the most successful theoretical frameworks in history, a model that described every known particle and force, except gravity, had to be revised. Evidence for oscillations began to accumulate in the late 1990s. The Super Kamiokande detector in Japan, a massive underground chamber filled with 50,000 tons of ultra-pure water, observed atmospheric neutrinos created when cosmic rays struck Earth's atmosphere. By measuring the number of muon neutrinos arriving from different directions, scientists found a discrepancy. Neutrinos produced on the opposite side of the planet, which had traveled through Earth, arrived in smaller numbers than those from directly above. The only explanation was that some of them had changed flavor during their journey. A few years later, the Sudbury Neutrino Observatory in Canada confirmed that the total number of solar neutrinos, counting all flavors, matched theoretical predictions. The missing neutrinos had not vanished. They had transformed. This discovery changed everything. It proved that neutrinos have mass, though incredibly small, less than a millionth of the mass of an electron. It showed that they could oscillate between flavors, a phenomenon governed by quantum mechanics on a cosmic scale. And it revealed that the standard model, for all its success, was not the final story. The equations that had predicted the behavior of every known particle had to be extended. The implications were enormous. Neutrino mass means that neutrinos could play a role in shaping the universe itself. They would have influenced the evolution of large-scale structures in the early cosmos, altering how galaxies formed. It also meant that new physics must exist, perhaps connected to phenomena such as dark matter or the asymmetry between matter and antimatter. If neutrinos can change flavor, perhaps they can also behave differently from their antiparticles, offering a clue to why the universe today is made almost entirely of matter. In 2002, the Nobel Prize in Physics was awarded to Masatoshi Koshiba and Raymond Davis Jr. for their pioneering neutrino experiments. In 2015, Takaaki Kajita and Arthur MacDonald received another Nobel for confirming neutrino oscillations. Their work closed one mystery and opened a dozen more. The ghost that Pauli had invented to preserve order had turned out to be an agent of disorder, forcing physicists to rewrite the laws of nature. The discovery of neutrino oscillations was not just a triumph of measurement, but of imagination. To detect neutrinos, scientists had to build instruments of almost spiritual patience detectors, so large and sensitive that they could record a handful of events per month. They buried them beneath mountains and in mines, filling vast caverns with water, heavy water, or liquid scintillator. They surrounded them with photomultiplier tubes that could detect a single photon of light. These devices turned the Earth itself into part of a cosmic laboratory, listening to the silent stream of particles passing through it. As the data grew, so did the mystery. The exact pattern of neutrino masses is still unknown. We can measure the differences between the squared masses of the flavors, but not their absolute values. We do not know which flavor is heaviest, or whether the pattern is normal or inverted. We do not know whether neutrinos are Majorana particles, that is, whether they are their own antiparticles. We do not know if they violate CP symmetry, a difference in behavior between matter and antimatter that could explain the cosmic imbalance. Every experiment deepens the puzzle. Each piece of data fits, but the overall picture remains incomplete. Neutrinos seem to sit at the crossroads of particle physics and cosmology, a bridge between the smallest and largest scales of reality. They connect nuclear reactions in the hearts of stars to the structure of the universe itself. They are both local and cosmic, ephemeral and eternal. The neutrino puzzle is not just about missing particles or adjusted equations. It is about humility. It reminds us that even when we think we have mastered the laws of nature, the universe can surprise us with something so small, so elusive, that it passes through the entire planet unnoticed. It reminds us that simplicity in theory often hides complexity in reality. And it reminds us that science is not the pursuit of certainty, but of understanding a journey in which every solved problem opens another mystery. The ghost particle that once saved the conservation of energy has now become a messenger from the edges of knowledge. It tells us that the universe is stranger than our mathematics can easily contain. The neutrino puzzle is no longer a problem to be solved, but a path forward, one that leads from the quantum heart of matter to the cosmic scale of everything that exists. The story of the universe cannot be told without the neutrino. Though it is among the smallest and lightest of particles, its presence is woven into the earliest seconds after the Big Bang, and stretches across the billions of years that followed. Neutrinos are not merely the ghosts of stars and reactors. They are relics of creation itself, survivors from the universe's first breath. Understanding their role in cosmology is to trace the connection between the subatomic and the cosmic, between the smallest scales of quantum mechanics and the largest structures of the universe. To imagine the universe when neutrinos first appeared, we must go back nearly 14 billion years, to a time when everything that exists today was compressed into a searing, dense plasma of particles and radiation. In those first moments, the universe was so hot that matter and energy were indistinguishable. Protons, neutrons, electrons, photons, and neutrinos all interacted constantly, colliding and annihilating in a state of thermal equilibrium. For the first few tenths of a second, neutrinos were as tightly coupled to the rest of the universe as light itself. But as the cosmos expanded and cooled, conditions changed. Roughly 1 second after the Big Bang, the temperature of the universe had fallen to about 10 billion degrees Celsius. At that point, the interactions between neutrinos and other particles became too rare to keep them in equilibrium. They decoupled, drifting free from the plasma, no longer scattering off electrons or nucleons. From that moment on, the universe was filled with a vast sea of neutrinos traveling freely through space, carrying with them the conditions of the cosmos at that precise instant. This ancient population, known as the cosmic neutrino background, is the oldest observable remnant of the early universe, even older than the cosmic microwave background, which formed about 380,000 years later when light itself was finally released. The existence of this cosmic neutrino background is one of the great predictions of cosmology. Though it has never been directly detected, its presence is inferred through its influence on the universe's evolution. Just as the cosmic microwave background carries an afterglow of light from the early plasma, the cosmic neutrino background carries an aftertaste of matter. Calculations show that for every photon in the universe today, there should be roughly 1.5 neutrinos of each flavor. That means there are about 330 relic neutrinos in every cubic centimeter of space, including the space you occupy right now. They are everywhere, moving at nearly the speed of light. But they are so low in energy and so weakly interacting that they pass unnoticed through planets, stars, and galaxies. The cosmic neutrino background has left its fingerprints on the large-scale structure of the cosmos. In the early universe, neutrinos were fast enough to escape the gravitational pull of small matter concentrations, smoothing out density fluctuations on small scales. This free streaming effect slowed the growth of structure, preventing tiny clumps of matter from collapsing too early. As the universe expanded and neutrinos cooled, they became less influential, but their early escape left a lasting mark. The distribution of galaxies, the formation of clusters, and even the pattern of ripples in the cosmic microwave background all bear the signature of neutrinos. Modern cosmological observations have turned these effects into precise measurements. The Planck satellite, launched by the European Space Agency, mapped the cosmic microwave background with unprecedented accuracy. By studying its subtle fluctuations, scientists were able to infer how many types of light particles, or relativistic species, existed in the early universe. The results confirmed what particle physics had long predicted: 3 families of neutrinos, no more and no less. The data also placed tight limits on the total mass of all neutrinos combined, showing that their collective mass must be less than about 1/10 of an electron volt. This tiny value demonstrates that neutrinos are light enough to remain nearly relativistic even today, still drifting through space as faint echoes of the Big Bang. In cosmology, small masses can have large consequences. Even such light particles affect how galaxies form and how matter clumps over time. By combining observations from the cosmic microwave background, galaxy surveys, and gravitational lensing, cosmologists can constrain the sum of the neutrino masses with remarkable precision. Future surveys such as the Euclid mission and the Vera Rubin Observatory will tighten those limits even further, perhaps revealing the absolute scale of neutrino mass before laboratory experiments do. In this way, the universe itself becomes the ultimate detector, recording in its structure the properties of the particles that shaped it. The role of neutrinos extends beyond the primordial past. Throughout cosmic history, they have been constant travelers, created in every nuclear reaction, every supernova, every collision of cosmic rays. In the hearts of stars, neutrinos carry away most of the energy produced by fusion, regulating stellar lifetimes and evolution. In supernova explosions, they release nearly all the energy of the collapsing core, triggering the shockwave that blasts the star's outer layers into space. Without neutrinos, many of the heavy elements on which life depends, carbon, oxygen, iron, would never have been dispersed into the galaxy. Even on a cosmic scale, neutrinos are agents of transformation. The cosmic neutrino background, however, remains the ultimate prize. Detecting it directly would be a triumph of both experimental ingenuity and cosmological insight. The relic neutrinos today are unimaginably cold, with energies of only a fraction of a milli-electronvolt. They move slowly compared to the speed of light, but their number is enormous. Experiments such as Ptolemy aim to catch them by using tritium, the same isotope studied in the K80 experiment. When a relic neutrino is captured by a tritium nucleus, it slightly alters the energy of the emitted electron, producing a signature that, in principle, can be measured. Success would provide the first direct glimpse of the universe as it existed 1 second after its birth. Neutrinos also hold the key to one of the deepest puzzles in cosmology: the imbalance between matter and antimatter. The laws of physics treat both almost symmetrically, yet the observable universe is made almost entirely of matter. One hypothesis, known as leptogenesis, suggests that in the early universe, decays of heavy neutrinos violated this symmetry, creating a slight excess of matter over antimatter. That excess, though minuscule, perhaps only 1 part in a billion, was enough to ensure that when matter and antimatter annihilated, a small remainder of matter survived to form galaxies, stars, and ultimately life. If leptogenesis is correct, the humble neutrino was the deciding factor in the existence of everything we see. The beauty of this idea lies in its unity. A particle born from the need to conserve energy in atomic decay turns out to be central to the cosmic balance of creation. From the core of the sun to the first second of the universe, the neutrino links the smallest scales of physics to the largest scales of structure. Its behavior reveals how quantum phenomena ripple outward into cosmic consequences. Today, neutrinos are part of every major cosmological model. They appear in the equations that describe the expansion of the universe, the formation of galaxies, and the synthesis of elements. They are measured not only in laboratories but in the patterns of starlight and in the gravitational dance of galaxies. In a sense, they have become both particles and principles, both specific entities and symbols of the deep connection between matter and the cosmos. The future of neutrino cosmology promises even greater revelations. As detectors grow more sensitive and sky surveys more precise, the interplay between particle physics and astronomy will tighten. Cosmologists will refine their measurements of neutrino mass and density, while particle physicists will explore the mechanisms that give neutrinos their mass in the first place. These two domains, once separate, now meet in the same equations and the same sky. If we ever detect the cosmic neutrino background directly, it will mark the final unification of cosmology and particle physics. We will have heard at last the whisper of the universe's first second, a sound carried not by light, but by the faintest of particles. It will confirm that every neutrino passing through us is not only a messenger from stars and reactors, but also a relic from creation itself. The story of neutrinos in cosmology is therefore not just scientific, but philosophical. It shows that what is smallest can shape what is largest, that invisibility can define reality, and that the universe carries memory in its very structure. The same particles that pass silently through your body at this moment once streamed freely through the newborn cosmos. They connect you, and everything you know, to the origin of time. In the end, neutrinos teach us that the universe is a continuum, not a collection of separate parts, but a single fabric of matter, energy, and history. They are the quiet evidence that everything is linked, the atom to the galaxy, the laboratory to the stars, the present to the beginning. To study them is to look not only outward into space, but backward into time, toward the instant when the universe first learned to be. The story of invisible matter begins with a paradox. When astronomers first looked into the great clusters of galaxies, they found that the visible stars and gas could not explain the motions they observed. The galaxies moved too quickly to be held together by the gravity of what was seen. Something else had to be there, something invisible, massive, and dominant. The universe, it turned out, was missing most of its mass. The first to notice was Fritz Zwicky, a Swiss astronomer known for his blunt manner and radical ideas. In 1933, while studying the Coma cluster, a vast congregation of galaxies about 300 million light-years away, he measured their velocities using Doppler shifts. The result shocked him. The galaxies were moving so fast that, without some hidden mass binding them, the cluster should have dispersed long ago. Zwicky calculated that the visible matter accounted for only a fraction of what was required. He called the missing component Dunkle Materie, dark matter. His conclusion was bold, but at the time, it seemed speculative. Astronomers lacked both the data and the instruments to test his claim. Decades later, in the 1970s, another observer confirmed Zwicky's suspicion on a galactic scale. Vera Rubin, working at the Carnegie Institution, measured the rotation speeds of spiral galaxies. According to Newtonian gravity, stars at the outer edges of a galaxy should orbit more slowly than those near the center, just as planets far from the Sun move more slowly than those close to it. Yet Rubin's results defied expectation. The rotation curves of galaxies were flat. The outer stars moved just as fast as those inside. The implication was unavoidable. Vast halos of unseen matter surrounded every galaxy, outweighing the visible stars by factors of 5 or more. What Zwicky had glimpsed in clusters, Rubin found in individual galaxies. The evidence began to accumulate from every direction. X-ray telescopes revealed hot gas in galaxy clusters, held in place by gravitational fields far stronger than visible matter could produce. Observations of gravitational lensing, the bending of light by massive objects, showed arcs and distortions around clusters that required unseen mass to explain. Later, measurements of the cosmic microwave background, the faint afterglow of the Big Bang, confirmed that only about 5% of the universe consists of ordinary baryonic matter, while roughly 27% is matter that does not interact with light. The remaining 68% is dark energy, a still greater mystery. The cosmos, it seemed, was dominated by darkness. Dark matter is not black dust or invisible gas. It is not made of atoms, and it does not emit or absorb radiation. It interacts only through gravity and, perhaps, through the weak nuclear force. Its presence is inferred from its effects from the way galaxies spin, the way clusters bind, and the way light bends as it travels through space. For all its elusiveness, it is far from rare. Dark matter outweighs ordinary matter by more than 5 to 1. Every galaxy, including our own Milky Way, is enveloped by a vast halo of it, a structure extending far beyond the visible disk. The stars are merely the luminous traces of this hidden framework. The question, of course, is what dark matter actually is. Over the past decades, physicists have proposed a range of candidates. The most widely studied are the weakly interacting massive particles, or WIMPs. These hypothetical particles would have masses many times that of a proton, and interact through the weak nuclear force, making them difficult, but not impossible to detect. If WIMPs were produced in the early universe, their abundance would naturally align with the amount of dark matter observed today, a coincidence so neat that it became known as the WIMP miracle. To test this idea, scientists built some of the most sensitive detectors in history, buried deep underground, shielded from cosmic rays and natural radioactivity. These instruments wait for the faintest whisper of a WIMP colliding with an atomic nucleus. The Lux Zeppelin experiment in South Dakota, the Xenon detector in Italy, and the Panda X experiment in China all use large volumes of liquid xenon, capable of capturing the tiny flashes of light produced by such rare interactions. Despite decades of searching, no definitive detection has yet been made, but the limits keep improving, closing in on the region where theory predicts WIMPs might lie. Other hypotheses have emerged as well. One involves the axion, a particle originally proposed to solve a problem in quantum chromodynamics, the theory describing the strong nuclear force. Actions would be extraordinarily light, but they could exist in such enormous numbers that they collectively form the dark matter halo. Experiments such as ADMX in the United States search for axions by attempting to convert them into photons in strong magnetic fields. Another possibility is the sterile neutrino, a heavier cousin of the known neutrinos that interacts only through gravity and mixing with ordinary neutrinos. If sterile neutrinos exist, they could explain both certain anomalies in oscillation experiments and the missing mass of the universe. There are more exotic ideas too: supersymmetric particles, primordial black holes formed in the first moments after the Big Bang, or entirely new forms of matter governed by forces beyond the standard model. Each proposal reflects a truth about dark matter. It is not only an astronomical mystery, but a gateway to new physics. Whatever it is, it cannot be made of the particles we know. Its discovery will require expanding our understanding of the fundamental building blocks of reality. For a time, some researchers wondered whether dark matter might not exist at all, whether the discrepancy could be explained instead by modifying the laws of gravity. Theories like modified Newtonian dynamics propose that gravity behaves differently at very low accelerations, potentially eliminating the need for unseen mass. But these models fail to explain the full range of evidence, especially the patterns observed in the cosmic microwave background and the behavior of galaxy clusters, like the Bullet cluster, where the separation between visible matter and gravitational mass is unmistakable. The simplest, most consistent explanation remains that dark matter is real, an invisible substance filling space and shaping the universe. Its influence is everywhere. Dark matter's gravity seeded the formation of galaxies and clusters in the early universe. Tiny density fluctuations in the primordial plasma grew over billions of years, drawing in ordinary matter, igniting stars, and creating the cosmic web we see today. Without dark matter, galaxies would never have formed. The universe would have remained a thin, diffuse fog. The stars we see are merely the luminous frosting on an invisible structure that defines the shape of everything. And yet, for all its importance, dark matter remains untouchable. We cannot see it, we cannot feel it, and we have not yet captured it. It is both the most ubiquitous and the most mysterious substance in existence. Its discovery will be one of the defining achievements of physics, not only because it will complete our inventory of the universe, but because it will open a window into a realm of phenomena beyond the reach of current theory. Dark matter reminds us that the universe is not what it seems. The luminous galaxies, the glowing nebulae, the bright stars, all are decorations on a vast, unseen framework. The visible universe is only the surface of a much greater reality. We live, move, and think within a cosmos whose true substance is invisible. The search for dark matter is therefore not just a scientific quest, but a philosophical one. It asks us to reconsider what it means to see, to know, and to exist in a universe that hides most of itself from our senses. If the invisible defines the structure of the cosmos, then understanding it is the key to understanding everything else. And just as neutrinos, once thought undetectable, were finally revealed, so too will dark matter yield to patience, precision, and imagination. The invisible may resist us, but it is not beyond reach. It waits, silent and omnipresent, for the moment when the instruments of humanity become sharp enough to see what the eyes cannot. Invisible messengers reach Earth from the farthest corners of the cosmos, not in beams of light, but as torrents of particles. They arrive silently, constantly, striking the atmosphere by the billions every second. These are the cosmic rays, high-energy particles that have traveled across unimaginable distances, accelerated by forces beyond human comprehension. Their existence reveals that the universe is not a tranquil expanse of stars, but a storm of invisible motion, where matter is hurled through space at nearly the speed of light. The story of cosmic rays begins not in space, but in the skies above Earth. In the early 20th century, scientists puzzled over why sensitive instruments discharge spontaneously, even when insulated from known sources of radiation. Many believed the culprit was terrestrial, perhaps radioactive material in the ground. But in 1912, the Austrian physicist Victor Hess set out to test this assumption. He ascended in a balloon carrying electrometers to measure ionizing radiation at different altitudes. As he rose through the atmosphere, the radiation increased rather than decreased. The source, Hess concluded, must be extraterrestrial. For this discovery that space itself bombards Earth with energetic particles, he would later be awarded the Nobel Prize. At first, no one could have imagined the power carried by these invisible visitors. Early detectors revealed that most cosmic rays are protons, hydrogen nuclei stripped of their electrons, along with a smaller fraction of heavier nuclei and electrons. As technology advanced, scientists began measuring their energies, and what they found was staggering. Some cosmic rays possess energies greater than 10 to the power of 20 electron volts, far beyond what any human-built accelerator can produce. A single proton can carry the kinetic energy of a thrown baseball, compressed into a subatomic particle, smaller than a billionth of a meter. These extreme energies hint at astrophysical engines of unimaginable intensity: supernovae, pulsars, black holes, or perhaps even sources we have not yet discovered. When a cosmic ray strikes Earth's atmosphere, it collides with a nucleus of nitrogen or oxygen, creating a cascade of secondary particles, pions, kaons, muons, and neutrinos that rain downward in all directions. These secondary showers can spread over kilometers, lighting up detectors at the surface or deep underground. Among the products of these collisions are atmospheric neutrinos, ghostly particles that pass effortlessly through the planet. Every second, billions of these neutrinos stream through your body, born from cosmic interactions miles above. They are a reminder that the universe is constantly whispering to us, in particles too small to see. These atmospheric neutrinos were once regarded as background noise, an interference in the search for other signals. Yet they became one of the most important tools in the history of particle physics. In the 1990s, detectors such as Super Kamiokande in Japan began studying atmospheric neutrinos in detail. They measured the number of muon neutrinos arriving from above created in the atmosphere and compared it to those arriving from below, which had traveled through the entire Earth. The results revealed something unexpected. The upward-going neutrinos were fewer than predicted, as though some had vanished on their journey. The only explanation was that they had changed identity. This discovery confirmed that neutrinos oscillate between flavors, proving they have mass and breaking one of the key assumptions of the Standard Model. Thus, cosmic rays, though born in distant astrophysical accelerators, played a crucial role in rewriting the laws of fundamental physics. At ground level, their descendants muons tell another story. Muons are unstable, decaying in microseconds, yet time dilation from their near-light speeds allows them to reach Earth's surface in abundance. Every minute, thousands of muons pass through every square meter of ground, through buildings, and through our own bodies. They leave faint tracks in detectors, and sometimes even in ancient rocks and ice. Archaeologists have begun using muon imaging to probe the interiors of pyramids and volcanoes, turning a cosmic phenomenon into a practical tool. These particles, born from invisible collisions high above, now serve human curiosity in ways Victor Hess could never have imagined. But where do the cosmic rays themselves come from? The answer depends on their energy. Lower energy, cosmic rays, the most common, are thought to originate within our galaxy. Supernova remnants, the expanding shock waves from dying stars, provide the perfect environment for acceleration. As charged particles spiral within magnetic fields, they gain energy with each reflection, a process known as diffusive shock acceleration. These cosmic rays fill the Milky Way, shaping its chemistry, contributing to the ionization of interstellar gas, and perhaps influencing the formation of new stars. At higher energies, the picture grows more mysterious. Some cosmic rays appear to come from beyond the Milky Way, perhaps from active galactic nuclei galaxies, with supermassive black holes at their centers, launching powerful jets of plasma. Others may originate in gamma-ray bursts, cataclysmic explosions that for a few seconds outshine entire galaxies. The most extreme events produce particles so energetic that they challenge the known laws of acceleration. Such particles are rare. Only a few strike each square kilometer of Earth per century. To detect them, scientists have built vast observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah, covering thousands of square kilometers with detectors. Each time a high-energy particle enters the atmosphere, these instruments capture its shower of secondary particles and reconstruct the energy and direction of the original cosmic ray. Every detection is a message from an invisible accelerator somewhere in the universe. The connection between cosmic rays and neutrinos is intimate. Wherever cosmic rays are accelerated, interactions with surrounding matter or radiation inevitably produce neutrinos. Detecting such neutrinos allows scientists to identify the cosmic engines responsible for the acceleration. Neutrinos, unlike charged cosmic rays, are not deflected by magnetic fields, so they point directly back to their sources. This relationship lies at the heart of multi-messenger astronomy, where cosmic rays, neutrinos, photons, and gravitational waves combine to tell the story of the universe's most energetic events. In 2017, this relationship was confirmed spectacularly. The IceCube Neutrino Observatory in Antarctica detected a high-energy neutrino whose direction matched that of a flaring blazar, a galaxy with a supermassive black hole emitting jets of radiation. At the same time, space-based telescopes observed a burst of gamma rays from the same source, TXS 0506 plus 056. This coincidence was not chance. It was the first time a specific astrophysical object had been identified as a source of high-energy neutrinos and, by implication, of cosmic rays. The invisible link between two of the universe's most elusive messengers had finally been revealed. Cosmic rays also teach us about the limits of the universe. At energies above about 5 times 10 to the power of 19 electron volts, interactions with the cosmic microwave background should sap their energy, creating a natural cutoff known as the Greisen-Zatsepin-Kuzmin limit. Observations confirm this effect, suggesting that the highest energy cosmic rays must originate within a few 100 million light-years. The universe itself imposes a boundary, not by walls, but by the sea of ancient photons that fills space. Even with these insights, mysteries remain. We still do not know exactly which objects produce the most energetic cosmic rays, or how nature accelerates them so efficiently. The identity of the particles themselves, whether they are mostly protons or heavier nuclei, continues to be studied. And though neutrino detections have linked some cosmic rays to specific sources, the full catalogue of cosmic accelerators is far from complete. The cosmos keeps its secrets well, yet each discovery brings us closer. Cosmic rays remind us that space is not empty, but alive with motion. They reveal that stars, galaxies, and black holes are not quiet or isolated, but constantly releasing torrents of energy. They also remind us that the invisible can be both destructive and creative, shaping the universe we see while remaining beyond sight. The atmosphere above us is a stage for cosmic drama, replayed endlessly, where particles born in distant galaxies meet the air of our planet and create cascades of light too faint for our eyes. We live under this invisible rain, and in a sense, within it. The same processes that fill our atmosphere with cosmic relics also give rise to the neutrinos that flow through every living being. The boundary between cosmic and terrestrial is blurred. The universe does not end at the sky, but continues through us, written in particles that cross the planet without resistance. Cosmic rays and atmospheric neutrinos complete the trilogy of the unseen. Neutrinos show us the invisible matter born in stars. Dark matter shows us the invisible mass shaping galaxies. Cosmic rays show us the invisible energy connecting them both. Together, they reveal a universe whose true character is not defined by light, but by motion, interaction, and gravity, by the unseen forces and particles that govern the structure of everything. The discovery of cosmic rays began as an accident, a curiosity about discharging instruments. Today, it stands as one of the pillars of astrophysics, linking particle physics, astronomy, and cosmology into a single narrative. In their invisible descent through the atmosphere, cosmic rays tell us that the universe is not static, that it is restless and alive, and that we, too, are part of that great unseen storm. The universe speaks in many voices. For centuries, we listened only to light. Every telescope ever built, from Galileo's glass tube to the most advanced observatories orbiting Earth, has been an instrument for collecting photons. Through light, we discovered the galaxies, measured their motions, mapped the cosmic microwave background, and even glimpsed the afterglow of creation itself. But light is limited. It can be absorbed by dust, scattered by gas, or trapped entirely inside dense celestial furnaces. To see deeper, to look inside the hidden engines of the universe, we need messengers that do not care about matter, that pass through stars and planets as though they were empty space. These are the neutrinos, the ghosts of the cosmos. The idea of observing the universe through neutrinos once seemed impossible. Neutrinos interact so rarely that even a dense detector might wait years for a single event. But the history of science has always been a story of turning impossibilities into discoveries. The first great success came in 1987, when a star in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, reached the end of its life. The collapse of its core triggered a supernova known as Supernova 1987A, one of the brightest in modern times. Long before its light became visible in the night sky, a handful of detectors buried deep underground recorded a burst of neutrinos. Over 13 seconds, 24 neutrinos arrived from the dying star. They were the first neutrinos ever detected from beyond the solar system. It was a small number, barely a trace out of the 10 to the power of 58 neutrinos released by the explosion, but it was enough to change history. For the first time, humanity had observed a cosmic event through particles rather than light. Those few detections confirmed that in a supernova, almost all the energy is carried away by neutrinos. They also arrived several hours before the light, proving that neutrinos could serve as early messengers of stellar death. That single event demonstrated the potential of neutrino astronomy. For decades afterward, scientists dreamed of building detectors large enough to catch neutrinos, not just from supernovae, but from distant galaxies, black holes, and cosmic collisions. To do so would require instruments of unprecedented scale, vast volumes of water or ice, buried deep underground, to shield them from background radiation. The goal was audacious: to turn the Earth itself into part of a telescope that could see with neutrinos instead of light. The 21st century made that dream real. Deep beneath the Antarctic ice, engineers and scientists built the IceCube Neutrino Observatory, a cubic kilometer of instrumented ice, embedded more than 2 kilometers below the surface. Thousands of light sensors, called photomultiplier tubes, were deployed along vertical strings in a transparent lattice. When a neutrino interacts with a nucleus in the ice, it can produce a charged particle moving faster than light travels through that medium. The result is a flash of blue Cherenkov radiation, faint but measurable. By recording the timing and brightness of these flashes across many sensors, scientists can reconstruct the direction and energy of the incoming neutrino. For years, IceCube waited, listening to the universe. Then, in 2013, it captured the first unmistakable signs of astrophysical neutrinos particles, so energetic they could not have been produced in Earth's atmosphere. They were given playful nicknames, Bert and Ernie, but their significance was profound. They marked the birth of high-energy neutrino astronomy. Unlike the low-energy neutrinos from the Sun or from supernovae, these neutrinos carried energies in the peta-electron-volt range, indicating origins in some of the most extreme environments in the universe. Each detection was a clue. The pattern of events suggested that the universe produces a steady flux of high-energy neutrinos, perhaps from active galactic nuclei, gamma-ray bursts, or colliding galaxies. The challenge was to trace any single neutrino back to its source, to connect a particle in Antarctic ice to an object millions or billions of light-years away. That breakthrough came in 2017. IceCube detected a high-energy neutrino arriving from the direction of a known blazar, a galaxy powered by a supermassive black hole whose jet was pointed directly at Earth. At the same moment, space-based telescopes observed a flare of gamma rays from the same object, designated TXS 0506 plus 056. The coincidence was too strong to ignore. For the first time, scientists had identified a specific astrophysical source of neutrinos. This event marked a turning point. Neutrino astronomy had become not just possible, but practical. By combining neutrino detections with observations of light and gamma rays, scientists could now study the inner workings of cosmic accelerators, the environments near black holes, where matter and magnetic fields interact violently. Unlike photons, which can be absorbed or scattered, neutrinos carry unaltered information from deep within these regions, offering a direct probe of their physics. The rise of neutrino astronomy also transformed the larger landscape of astrophysics. For the first time, the universe could be studied through multiple messengers: light, neutrinos, cosmic rays, and gravitational waves. This multi-messenger approach allows scientists to weave together different signals from the same event, creating a more complete picture of the cosmos. When gravitational waves from colliding neutron stars were detected in 2017, telescopes across the electromagnetic spectrum turned to observe the event. Neutrino detectors stood ready as well. Though no neutrinos were seen from that particular merger, the coordination demonstrated the potential of a unified, multi-messenger network capable of catching the universe in the act of creation. The tools of this new astronomy are vast and still growing. IceCube continues to operate at the South Pole, while in the Northern Hemisphere, the KM3 net detector in the Mediterranean Sea is under construction, using deep water as its observing medium. Japan's Hyperkamiokande, now being built, will hold nearly 260,000 tons of ultra-pure water, expanding the reach of neutrino detection for both astrophysics and fundamental physics. In the United States, the Deep Underground Neutrino Experiment, DUNE, will use enormous liquid argon detectors to study neutrino oscillations and to catch neutrino bursts from distant supernovae. Together, these observatories form a global network listening to the silent language of the universe. Neutrino astronomy is still young, and many mysteries remain. The origins of most high-energy neutrinos are still unidentified. The flux observed by IceCube suggests a variety of sources, perhaps including star-forming galaxies, galaxy clusters, or, as yet, unknown phenomena. Each detection adds a piece to the puzzle, refining our understanding of how the universe accelerates matter to extreme energies. And as detectors grow more sensitive, the dream of mapping the sky in neutrinos, of seeing the invisible, comes closer to reality. What makes neutrino astronomy remarkable is not only its technology, but its philosophy. It represents a shift in how we perceive the universe. For most of human history, we have looked outward and seen beauty in light, the glow of stars, the shimmer of galaxies, the radiance of nebulae. Now we have begun to listen to the darkness. The neutrino is the quiet messenger, the one that slips through walls of matter and emerges unscathed from the hearts of cataclysms. To study it is to listen to what the cosmos says when all else is silent. The next generation of detectors will turn that silence into song. They will measure neutrinos from supernovae, from active galaxies, from the remnants of the Big Bang itself. They will help determine the absolute masses of neutrinos, probe the symmetries of nature, and perhaps even uncover new particles or forces. Every improvement in sensitivity expands the conversation between humanity and the universe. Neutrino astronomy closes the gap between the visible and the invisible, between the known and the unknown. It allows us to see without seeing, to detect without touching. It proves that even the faintest signals, the rarest interactions in the most distant ice, can change our understanding of everything. It is a triumph of patience, of collaboration, and of imagination. We now live in an era where the universe no longer hides behind light alone. It reveals itself through gravity, through matter, through invisible streams of particles passing constantly through our world. Neutrinos, once called ghost particles, have become the key to unlocking the hidden cosmos. Each one that reaches a detector carries the story of a place where light could not escape, and together, they remind us that the universe is not silent, only subtle, a place where the faintest whispers can echo across eternity. If only we learn how to listen. Humanity stands at a new edge of discovery, not an edge defined by distance or direction, but by perception itself. For the first time, we know with certainty that most of the universe is invisible. The light of stars and galaxies, the brilliance that fills our telescopes and photographs the cosmos in glory, accounts for less than a small fraction of what exists. The rest, the overwhelming majority, is hidden in forms we cannot see: neutrinos, dark matter, and dark energy. This realization is both humbling and empowering. It means that the universe is far larger and stranger than our senses can comprehend, yet it also means that our tools, our intellect, and our curiosity have reached far enough to recognize what we cannot yet perceive. The future of this invisible frontier begins with precision. The questions that remain about neutrinos are among the most profound in physics. We now know that neutrinos have mass, but we do not yet know how much or why. Their masses are so small that they evade direct measurement, but experiments such as Katrin, the Karlsruhe tritium neutrino experiment in Germany, are approaching the threshold. KATRAN studies the electrons emitted when tritium decays, searching for the subtle influence of neutrino mass in the energy spectrum. Each refinement brings us closer to the answer. Future experiments like Ptolemy hope to go further still, attempting to detect the cosmic neutrino background, the oldest neutrinos in existence. Relics from the first, second, after the Big Bang. To capture them would be to touch the moment of creation itself. At the same time, physicists continue to search for one of the most elusive processes ever proposed: neutrinoless double beta decay. In this rare form of radioactive decay, 2 neutrons in an atom would transform into 2 protons and 2 electrons, with no neutrinos escaping. If it occurs, it would mean that neutrinos are their own antiparticles, that they are Majorana particles, capable of annihilating themselves. Such a discovery would not only rewrite our understanding of particle physics, but also explain one of the deepest mysteries in cosmology: why the universe is made of matter rather than antimatter. If neutrinos once tipped the balance in the earliest moments of time, they may be the reason anything exists at all. Beyond neutrinos, the invisible frontier stretches into the domain of dark matter. The search for it continues in underground laboratories, deep beneath mountains and deserts, where detectors filled with liquid xenon or argon wait in silence, for the faintest flash of light or ripple of charge. The Lux Zeppelin experiment in South Dakota, the Xenon detector in Italy, and the Panda X project in China are among the most sensitive ever built. Each hopes to capture the tiny signal produced when a dark matter particle collides with an atomic nucleus. So far, no confirmed detection has occurred, but each experiment narrows the possibilities, closing in on the truth. If dark matter consists of weakly interacting massive particles, discovery could come at any moment. If those particles are not found, the search will turn to other candidates. Actions, hypothetical particles proposed to solve a problem in quantum theory, could exist in vast numbers, forming invisible halos around galaxies. Experiments like ADMX attempt to detect them by converting them into microwave photons inside strong magnetic fields. Another possibility is that dark matter consists of sterile neutrinos, heavier cousins of the known neutrinos, that interact only through gravity and mixing. Still more radical ideas propose primordial black holes or completely new particles that do not fit within the standard model. Whatever the outcome, the search will not end in disappointment, because every null result sharpens the map of what is possible, guiding us toward the next breakthrough. The invisible frontier also extends to the largest scales of the cosmos. The European Space Agency's Euclid mission and the Vera Rubin Observatory in Chile will map the positions of billions of galaxies, tracing how their distribution changes over time. Subtle distortions in these maps will reveal the influence of dark matter and dark energy on cosmic structure. From these patterns, scientists hope to deduce the behavior of gravity across the universe and perhaps glimpse new physics operating on the grandest scales. The cosmos itself becomes an experiment, and its structure the record of every force that has shaped it since time began. Meanwhile, neutrino astronomy will continue to grow. The next generation of detectors, Hyperkamiokande in Japan, IceCube Gen 2 at the South Pole, and KM3 Net in the Mediterranean, will listen to the universe with unprecedented sensitivity. They will catch neutrinos from supernovae across the galaxy, from active galaxies billions of light years away, and perhaps from the first moments after the Big Bang. Each event will add to the cosmic symphony, turning what is now a trickle of detections into a steady stream of data. In the coming decades, it will be possible to map the sky not only in light, but in neutrinos, creating a new kind of atlas, a chart of invisible messengers. The merging of these fields, neutrinos, dark matter, cosmic rays, and gravitational waves, is creating a new era of multi-messenger astronomy. When a distant event occurs, such as a neutron star merger or a black hole feeding frenzy, it sends out more than light. It sends out gravity, neutrinos, and particles. Detecting all of them together allows scientists to reconstruct the full story of the event, from the initial collapse to the release of energy across all channels. In this way, the invisible frontier is becoming the key to a complete understanding of the cosmos. But this future is not only about technology, it is also about philosophy, about what it means to live in a universe that is mostly unseen. For centuries, our concept of reality has been tied to light. We believed that what we could see was what existed. The discovery of the invisible universe has overturned that assumption. It teaches that the true structure of reality is not limited to perception, but extends into realms our senses cannot access. Science, at its heart, is the extension of perception, the building of instruments that let us see what eyes cannot and hear what ears cannot. Every detector, every observatory, every calculation is a form of vision that reaches beyond human biology into the deeper fabric of existence. The invisible frontier also reveals something profound about our place in the cosmos. We are made of the rarest material. Ordinary matter, the atoms of hydrogen, carbon, and oxygen that make up our bodies, accounts for less than 5% of the universe. We are, in a literal sense, the luminous residue floating on a sea of darkness, and yet, it is this rare matter that has achieved consciousness, built tools, and begun to understand the invisible majority that surrounds it. In studying the unseen, we are the universe becoming aware of itself. The next century will bring discoveries that today seem as unreachable as the neutrino once was. Perhaps we will identify the nature of dark matter, or measure the cosmic neutrino background directly. Perhaps we will find new particles that bridge the gap between the visible and the dark. Perhaps we will even learn to manipulate these particles, turning the invisible into a tool of technology, as profound as electricity or magnetism once were. The path forward will not be easy. Progress will depend on patience, collaboration, and creativity, the same qualities that led humanity from the first spark of curiosity to the vast scientific enterprise of today. The invisible universe is not a place to visit, but a reality to perceive. It surrounds us now. Every second, trillions of neutrinos pass through our bodies, silent and indifferent. Every moment, Earth moves through a halo of dark matter, unseen, yet gravitationally present. Every instant, cosmic rays collide with the atmosphere, sending showers of secondary particles cascading through the air. We live in a constant interaction with the invisible, whether we know it or not. To study these hidden forces is to participate in one of the greatest adventures in human history. It is to extend the reach of knowledge beyond the limits of light, to prove that what is invisible is not unknowable. The frontier is vast, but we have already crossed its threshold. The instruments are built, the theories are refined, the data continues to flow. Every discovery deepens the mystery, and every mystery deepens our understanding of what it means to be part of this universe. Perhaps that is the true gift of the invisible frontier, not the answers it promises, but the perspective it offers. It reminds us that knowledge is always incomplete, that wonder is never exhausted, and that humility is the truest form of wisdom. The invisible defines the universe not because it hides from us, but because it invites us to keep searching. The stars may light the night sky, but it is the darkness between them that gives meaning to their glow. And so the journey continues. The neutrinos still stream through us. The dark matter still binds the galaxies. The cosmic rays still fall, carrying the energy of distant cataclysms. The universe remains vast, silent, and filled with secrets. Yet we listen now, with new instruments, new minds, and a new understanding that even the unseen can be known. In that knowledge lies the future, the frontier, not of distance, but of awareness, where the invisible becomes the key to reality itself.